Hello and welcome to this FMSP online revision recording for the MEI specification, Module D1, Decision Mathematics. The topic is algorithms, and under that heading in the specification we find 4 sections. The first says that you should be able to interpret and apply algorithms presented to you in different formats, perhaps as a flowchart, maybe just in written text, and perhaps looking a bit like a computer program in pseudocode. Then you ought to be able to develop and adapt an algorithm. And there's particular ones you should recognize from this list: sorting and packing. The names of these sorting algorithms should be familiar to you, as are the packing algorithms, I hope, but you will get a reminder about the sorting algorithms, but should know the packing algorithms from memory. Now section 3, complexity. Algorithmic complexity. For that we need to consider the worst case scenario. The graph with the greatest number of edges, a complete graph, for example. And we're thinking about what happens to the size of the problem. As the problem increases in size, how much longer does it take? For quadratic complexity, doubling the size of the problem quadruples the solution time, because 2 squared is 4. Tripling the size of the problem would mean the solution time is multiplied by a factor of 9, which is 3 squared. And then there's 3 in particular that you should know about. So let's have a look on the next page to consider the complexity of these. And here's a reminder about the big O notation and different kinds of complexity. I shan't read this all out, and just a reminder at this stage, you can always pause the recording if you want to take longer over reading a slide. But down this list we see Dijkstra's algorithm with quadratic complexity and Kruskal's and Prim's with cubic complexity. Okay, let's look at some examination questions then. And here is one quite typical question where an algorithm is defined. We've got these steps to follow, and we're given 2 different sets of input to feed into the algorithm. There's quite a few marks here, so we do need to show very clearly that we're following the algorithm, and every step of our thinking needs writing down. And quite typically we have a part at the end where you have to review the algorithm and work out what you think the algorithm is achieving. So let's do that. Here's the algorithm again, and part 1 asked us to start with input 3 on the left and 8 on the right. Now then, my advice to you always with these algorithms, especially when it's one you haven't seen before, is to read it very carefully and follow it in the most methodical, plodding method that you can. So step 1, write down the 2 numbers side by side on the same row, on the same level. Step 2, beneath the left-hand number, write down double that number. Beneath the right-hand number, write down half of that number, ignoring the remainder. Repeat that until the right-hand number is 1. So we'll double this one, and we'll halve that one. It's still not equal to 1 over here. We'll double this one, and we'll halve that one. And now we've reached 1. So we can go on to step 4. Delete those rows where the right-hand number is even. Well, that's the first 3 rows, in fact. Add up the remaining left-hand numbers. This is the result. Well, actually, there is only one number over there, and it's 24. So there's the result from this algorithm. Let's do the second set of input. This time we're asked to start with 26 and 42. Well, that's a bit more challenging because the numbers are bigger. But let's carry on exactly as before. Write the numbers side by side. Beneath the left-hand number, write down its double. Beneath the right-hand number, write down half of it. So 26 doubles to 52, and half of 42 is 21. Repeat step 2 until you get a 1 on the right. So double 52, 104, and half of 21. Ignoring any remainder. So should be 10.5, we'll just write 10. Do it again. 208 and 5. We're waiting until we see a 1 on the right hand side. Double it again. 416, and half of 5 is 2.5. Ignore the remainder, it's 2 that we write down. Double this again. 832, and half of 2 is 1, so we can now stop. Go on to step 4. Delete those rows where the right hand number is even. Well, I've got to be a bit more selective this time, so it's that because of the 42, but the 21 can stay. That goes because of the 10, but the 5 can stay. This one goes because of the 2, but the row with a 1 can stay. So I need to add up the 3 remaining numbers, and I end up with 1092. Well, I'm sure you've recognized this in fact, because you should have seen this before. It is in the textbook in the first chapter, in fact. So for our final mark for section 3, where it says write down what the algorithm achieves, I expect you've spotted that it's multiplication. So I'll write a sentence that says that the algorithm multiplies the two numbers. If you have a calculator handy, you might just want to check that 26 times 42 is 1092, but you may of course recognize this, as I said, as Russian multiplication from chapter 1 of the textbook. So just a comment on the marking of this. There's 3 marks for doing the working for part 1. One mark is for doubling and halving, so that's obeying one of the instructions. Another mark is for deleting the unwanted rows, so that's again following one of the steps of the algorithm. And the third mark is for getting the right answer. On the right, it's the same, a mark for halving and doubling, and a mark for deleting the rows, but whereas last time it was simply a mark for deleting everything and writing down 24, which is rather simple, this time you've got to delete the right rows and add up the correct numbers. So there's 2 separate marks for that, and a final mark for the right answer, making 4 marks for that part. And lastly, 1 mark for recognizing that the algorithm multiplies the 2 numbers. Okay, let's go on to another question then. There's a lot to read here, but everything in the box you'll see on another slide. So here is an algorithm, and it tells us it's for drawing 2 straight lines. If certain conditions are met, and I notice straight away looking down here there are places where division by A and D and B and E come into play, and of course you couldn't therefore have any of those being 0. So we have conditions up here about the values of the variables. There's also C and F, which neither of those should be 0, and that's a condition to do with the fact that the graph should not go through the origin, which is significant, as you'll see from the last part of the solution. Okay, so what we're going to do is follow this algorithm for the numbers they give us to start with. There's 7 marks for doing that, so it's quite a substantial process just to follow the algorithm through correctly. And then typically at the end, what do you think the algorithm is doing? In this case, there's a question saying, why do you think it might be useful if you were doing linear programming? Well, let's see what the algorithm does and see if we can work out why that would help us with linear programming. So here we go then. I've copied out most of the algorithm apart from the last step about drawing the graph, because we have to work out some values. Okay, I'm going to copy in here the values they asked us to start with, which is A is 1, B is 5, C is 25, D is 10, E is 2, and F is 85. So those are simply the numbers listed in the question which we're asked to use as input to the algorithm. Now let's follow the algorithm, and I'll say it once again: follow the algorithm simply step by step in the most systematic, plodding way, reading every line carefully and doing every step in turn. And I'm going to write down on the right hand side here enough evidence so that even the stingiest marker can see that I've followed the algorithm. Okay then. I've fed in A, B, C, D, E and F. Line 1 defines the variables and says A, B, C should be greater than 0. Yep, that's okay. Line 2 explains that I would get an equation out of this. The equation would be 10x plus 2y is equal to 85. So we're talking about straight lines, and I'm checking that D, E and F are greater than 0. Yes, yes, yes. Okay, on with the next step of the algorithm. Let x be the minimum of c over a and f over d. Okay, I better think about that. What's c over a? 25 divided by 1, 25. And f over d, 85 over 10, 8.5. Okay, x has to be the minimum of those two, which is clearly 8.5. Okay, let's carry on with y. Let y be the minimum of c over b, 25 over 5. 25 divided by 5 is 5. And f over e, 85 over 2. Well, that's 42.5. And which is the smaller of those? 5. Good. On to the next part. If x equals c over a, well, hang on a minute. C over a was 25 over 1, which is 25. No, it wasn't that. Okay, I can ignore the rest of that line. If x equals f over d, let me just remind myself, was it? F over d is 85 over 10, 8.5. Yes, so I'm now going to obey the instructions on this line. Then x star, I'm going to work that out in the box here, is f, that's 85, minus e times y, 2 times 5, divided by d, and d is 10. 85 take 10, that's 75 over 10, 7.5. And on to y star. Y star is c, that's 25, minus a, which is 1, times x, which was 8.5. And that's all divided by b, which is 5. I have to think about that. 25 take 8.5. That's 16.5. Divide that by 5. Well, it's not nice, but it is fairly tidy. It's 3.3 exactly. Okay, I've followed this algorithm, and I have the answers for x, y, x star, and y star. And let me say that out of the 7 marks for the algorithm, 4 of them are for getting this far correctly. And you can see there's all the evidence you need that the algorithm has been followed. Okay. Well, remember these values. We'll need them again in a moment. This is the latter part of the algorithm. Draw an x-axis labelled from 0 to x and a y-axis labelled from 0 to y. Okay, well, let's do that. And I've prepared one here, and as x was 8.5, I've used a scale which allows me to get up to 8.5 on here. And although it says go up to 8.5, I've put 9 on there just so I can see in a moment where 8.5 is on my scale. Okay. And then a y-axis labelled from 0 to y. 0 to y. And y was 5. 1, 2, 3, 4, 5. And do you know, I'm going to just remove that 9. It did say label it from 0 to x, so perhaps I will just label 8.5 as the last point on my scale and strictly obey the algorithm. Okay then, I've got to join 0y to x y star, and I've got to join x star y to x 0. I think I'm just going to have to refresh my memory about what all these values were. So clearly that's 0, and this one's 0. X is 8.5, and y is 5. X star is 7.5, and y star is 3.3. So there we go. Oh, I've missed out a y, 5. So I need to join 0.5 to 8.5, 3.3. 0.5 to 8.5, 3.3, and of course I would, if I had a ruler available to me in the exam, be very careful to do this with a ruler. Forgive me doing it freehand for now. I'm just going to label that point so they know what it was. 8.5, 3.3. Okay, second instruction. 7.55, so that's 7.5. I need to go all the way up here to 5, which I think is there. And I need to join that to 8.50. Well, that's down here. Okay, and that's, oh, not very straight. With a ruler it would have been wonderful. Well, how would the marking of that worked? First of all, for getting the scales correctly, in other words obeying the instruction about the scales, there's a mark. And then secondly, for drawing the correct lines on the graph, there's a mark each. That's 7 marks in total for following the algorithm. And now we have one last part, which is the question about why you might use this algorithm if you were doing linear programming. Well, I guess they're trying to hint then that perhaps this is the feasible region that you might get if these lines were our constraints. And notice the way the graph's been drawn, these intersections are at the extremes of the axes, which is making the feasible region as big as possible. And of course you may well use that technique where you draw the feasible region by finding the intersections on the two axes, and this intersection is fine, but the other intersection looks like it's going to be way off to the right. And again, for this line, the intersection is going to be way up the y-axis. So this has helped us draw the scales in such a way that the feasible region is a sensible size. So I'll finish off with a sentence that says that. I think it gives a good choice of scale, so that the feasible region, which I'm guessing is going to be that enclosed beneath and to the left of those lines, is a sensibly large size. And there's one final mark for making that kind of comment about the region and the size of the region. Well, I hope that's been a helpful reminder about following algorithms. Don't forget to look at the rest of the recordings in this series.